Okay, so hello again for the lecture course on quantum gravity. So we are approaching steadily the end of the term, and you have swallowed already a lot of formalism, the covariant approach, the canonical approach with metric variables, with loop variables. So you should at least now at the end have, 2 sessions where you see the applications. And today I talk about the quantization of black holes, and next week on quantum cosmology. Now, of course, I cannot in one lecture do just full justice to this whole topic, because you could have a whole semester just talking on quantization of black holes. So this is more an introduction and a set of appetizers, so that if you find this applications very interesting, then you can look it up in my book or elsewhere and the references and study the details. This is a one-session version of a big and still up-to-date topic where many people in the world, in all continents, contribute to the understanding of quantum black holes. Now, black holes I of course introduced in my relativity class, and you have here the so-called no-hair theorem, as John Wheeler called it, which means that in the context of Einstein-Maxwell theory, which means general relativity coupled to electromagnetic fields, all stationary black holes, so once they have finished their collapse, are characterized solely by 3 numbers, independent of their initial state. So in the initial state is very complicated. So stars, they have a lot of have many degrees of freedom, many hairs, so to speak. And if they end up in a black hole, not all end up, but if they do, they are just characterized by 3 numbers. So this means that in Einstein-Maxwell theory, all stationary black holes are characterized by the 3 parameters: m, the mass, then the angular momentum, and we also use this small a, which is the reduced angular momentum J over m, and the electric charge, if there is any. Yeah. So, okay, no hair means more precisely, these are 3 hairs. They are left, but out of these many hairs, this is what is left. So only 3 parameters. So this is a very powerful theorem, and it means that black holes, in a sense, are much simpler than other astrophysical objects. Because other astrophysical objects, they have many degrees of freedom. Okay, so that's one important property. Now, black holes have a horizon, and this horizon has an area, and this we call capital A. And there's an important theorem that Stephen Hawking proved in 1971. And he proved that if you make any changes with black hole, throw things in or whatever, basically things in, then the area can only increase but not decrease. It can stay the same, but it will not increase. Of course, this also holds for stationary black holes. I don't write it down all the time. The assumption is, of course, cosmic censorship. Recall, cosmic censorship means that from generic initial conditions, there are no naked singularities formed. That is, all singularities are covered by a horizon. And this is also proved and taken in the proof as an assumption. Now, okay, this is a differential geometric property. Still, you might think, there's another quantity in physics where we know that it cannot decrease, at least for a closed system, that it's the entropy. So there is at least a formal analogy with ds. So this is the entropy for a closed system. Okay, you might say, well, this is just an accident and it has nothing to do. But then you notice there are in fact analogies in black hole physics to all laws of thermodynamics, not only the second law. So this was proven beginning of 70s by Bardeen, Hawking, and others. And these are the followings: analogies to all laws of thermodynamics. Okay, the second law is already written down here, so that it's the second law. Now the first law says that temperature is constant on a body in thermal equilibrium, and in fact there is an analogous quantity in black hole physics that also has such a property, namely the surface gravity of a black hole. One can prove that it's constant all along the horizon, and this is, you can call, the zeros law of thermodynamics. So that T is analogous to kappa. No, kappa is the, if you recall from GR, is the surface gravity, and this is constant on the event horizon. For example, if you have Schwarzschild black hole, they have a simple expression for kappa. So you have kappa, you can write in, okay, it's 1/4 gm. C, speed of light, is equal to 1. And you also can write it in the form g times m over rs squared, where rs is the Schwarzschild radius. So you see it has this Newtonian expression of an acceleration. Gm over r squared, you know from Newtonian theory. This is why it's called the surface gravity or surface acceleration. Of course, in Kerr black hole, it's more complicated. Then the first law of thermodynamic. Well, usually that's the energy law, and in this case we have the following. We can prove dm is kappa over 8 pi g dA plus omega h dj plus phi dq. Okay, J and Q have introduced, so the electric charge and the angular momentum, if there's some. And this is the angular velocity. And this is the electrostatic potential. Yeah, and the usual form that you learn in the classes is that dE is equal to T ds minus P dV plus mu dN. And then then of course E definitely is analogous to M. You could write mc squared, then you have an energy. This here, if you tentatively identify gamma with T up to a factor and A with S, then it's clear that these two terms are analogous. Now this here corresponds more to the chemical potentials. So we have here these two terms here. So there is no analogy here to this volume term. So the volume does not play a role in the black hole law. Okay, so the third law of thermodynamics usually means that the temperature cannot be lowered down to absolute zero in a finite number of steps. That's what Nernst in around 1905 proved. So that's the third law. It means, and okay, if T corresponds to kappa, it means that kappa equals 0 cannot be reached in a finite number of steps. And this can be proven, yeah. I mean, there's a debate how general these proofs are, but at least some straightforward proofs, say Gedankenexperiments, where you, like in classical thermodynamics, you throw things in and you play around with them, then you can do whatever you want. I mean, kappa equal to 0, say for a rotating black hole, would mean the extremal black hole. So you may try to extract angular momentum to reach kappa equals 0, or if it's charged, to extract charge. You can do that, but you will never reach kappa equals 0. Okay, so there are these analogies, but at that time, say around 1973, I think this is when this was proven. No one, or almost no one, believed that this is more than a formal analogy. Why? I mean, because thermodynamics is based on statistical mechanics, on the microscopic picture of atoms and molecules, and here we deal with geometric objects. So we deal with space-time, with differential geometry. So what should that have to do with each other? Well, there was an exception. A student of John Wheeler in Princeton, Jakob Bekenstein, he thought differently. He entertained the idea that these are not just analogies, but that black holes really have, say, an entropy and really have a temperature. So why? Well, the reasoning was the following. So John Wheeler asked him, okay, what happens when a cup of tea is thrown into a black hole? And then it seems black hole has the cup of tea has a certain entropy. You calculate maybe in experimental physics 1 course if it has a certain, and when you throw it away, then there's no sign left. No, of it. I mean, it just has these three numbers, and there is no entropy or temperature. So you could violate in the universe the second law just by throwing things into the black hole. Can that be? Bekenstein thought that cannot be, and so he proposed the idea that black holes have entropy. Okay, so if this is the analogy here, A and S, then I mean from this here you would make an ansatz that S is then some function of A. And it's clear from that here, from this analogy, that kappa over 8 pi g dA corresponds to T ds. And if you make that ansatz, okay, then ds would be f prime of A dA. So that from here you can get T is kappa over 8 pi g f prime of A. Of course, this must be positive. I mean, temperature must be positive, which means that f prime of A must be positive. Okay, so the simplest would certainly be to assume that the temperature does not explicitly depend on the area. And you would just have then f prime is equal to 1, say, and f is proportional to A. But there are also Gedankenexperiments that Bekenstein made, so it's still entertaining to read this Gedankenexperiment now more than 50 years ago, like this Gedankenexperiment that Sadi Carnot, for example, made for the Carnot engine and these kind of things. And he concluded that actually F should be linear in A, because otherwise you can violate the second law. So I cannot, of course, do justice to this here, because I have no time to discuss Bekenstein's Gedanken experiments, but I tell you, so Gedanken experiments suggest, okay, it's only a suggestion, it's no proof, that F of A, okay, is a factor that one cannot calculate by just Gedanken experiments, but it's proportional to A. But if we measure this in units of Boltzmann's constant, so, or setting Boltzmann constant equal to 1, if you like, then if it's proportional to A should be compensated by a fundamental variable with units length squared. And classical relativity does not have such a unit length squared fundamentally, but you have one when you take the h bar quantum theory into account. And this is why the ansatz is here that you divide by the Planck length squared. And this, of course, brings h bar into play, and you will see then that this is justified, that the exact calculations bring this into play. So this brings h bar into play. Okay, and the question is about this numerical factor. Now, as I said, no one, or very, very few people believe that. And also Hawking did not believe that. And in attempts to disprove this claim by Bekenstein, they actually found that it is correct. And that black holes, in fact, are not black after all when they when quantum theory is into account, but they radiate. And they radiate with a thermal radiation. They have a temperature. So that is Hawking's most celebrated result. So Hawking in 1975. So he used quantum field theory on the background of an object that collapses to a star. So that's not a quantum gravity calculations, it's a quantum calculation, but on the background of a star collapsing to a black hole. No? So black holes have a temperature. So he used quantum field theory. Let me use that acronym QFT on the background of an object collapsing to a black hole. And in this he found that they have a temperature, and it's called then TBH, so you can read a BH as a black hole, or also as Bekenstein-Hawking, if you like. And this usually it's called the Hawking temperature. It's h bar kappa over. Now I introduce Boltzmann's constant 2 pi k. So I think also a c is there, if I'm not mistaken. But let us have c equals 1. So that's the famous general formula for any stationary black hole, no? Not necessarily a Schwarzschild. So that's the Hawking temperature. I mean, for Schwarzschild black hole, I already gave the expression in chapter 1. So Schwarzschild we have a TBH is, now I use the C, I think here's the C, just for completeness, h bar C cubed to 8 pi kb. So all the units are correct. I mean, if you make formal manipulations, I mean, the unit, you can set these things to 1, but if you make numerical estimates, then of course the units should be correct. So that's the famous formula, and if you insert the units, then you find this is approximately 6.17 times 10 to the minus 8 if you measure masses in solar masses, Kelvin. That means for a black hole with mass, a couple of solar masses, they have, I mean, if you have a collapse, then the resulting black hole has at least 3 or so solar masses. But you see, this is a tiny temperature, and this is much smaller than the 3 Kelvin background radiation in the universe. So for astrophysical black hole, much more goes in from the CMB photons than goes out. So you cannot hope to measure it for astrophysical black holes. It's much too small. But nevertheless, it's non-zero. And if you had black holes with small mass, and I will say something on them, then you could have a high temperature in principle. Already in chapter 1, I mentioned that there's an analogous effect shown by Bill Unruh. Actually, after Hawking, although conceptually this would have been before, but because you can prove a similar effect in flat space-time for an accelerated observer. Acceleration and gravity is locally related due to the equivalence principle. So you may not be too surprised that something like that exists for an accelerated observer. So if you have a Minkowski vacuum, just empty state in quantum field theory, and you move through this, not with a constant velocity, but with a constant acceleration, then you see particles. And you see them distributed with a certain temperature. And this is the Unruh or Unruh-Davis temperature. I think I called it DEU. This stands for Davis-Unruh because when he proved this with detectors, but formally it was already there, by Davis H bar A over 2 by KB C. And you see very clearly, that this is not an accident. This relation. This has nothing to do with black holes, and the only difference is here you have the surface gravity or surface acceleration of a black hole, and here you have the usual acceleration with your rocket when you accelerate through empty space. Also, this is very small. It's only 4.05 times 10 to the minus 25. A measured in meters per second squared, Kelvin. So you see for everyday accelerations, then this is a very small temperature. But you can have high temperatures, for example, in accelerators, and people have looked for this effect there. Actually, a similar effect has been seen for circular acceleration, but this is not a thermal effect. The thermal effect is for linear acceleration, and there it has not been directly observed. But no one doubts that it exists, and if directly measured, it would also give further support to this formula here. Now, because the temperature of a black hole is not zero, it radiates, and of course we assume energy conservation. So when it radiates, then it radiates away energy. But you see here from that formula here, say we restrict ourselves to the Schwarzschild case, the mass is in the denominator. So if it radiates, then of course the energy comes from the mass, from mc squared. So m becomes smaller. But if m becomes smaller here, t becomes bigger. So this is not like your cup of tea, which is very hot and emits and becomes cooler. Of course, otherwise you would be very surprised. It's here the opposite. So you radiate with a temperature, but it becomes hotter by radiation. And this is an effect typical for gravity. So TBH is unequal 0, which means that black holes, I use this acronym, black holes have a finite lifetime. And you can easily estimate this. I mean, the exact calculation is a bit more involved, but you can estimate by using Stefan Boltzmann's law. Yeah, so let us do this estimate. So we have the change in the energy, what is radiated. Okay, what a decrease in the mass, in the energy, of course, must be radiated, and this is, according to Stefan Boltzmann's law, proportional to minus is the radiation minus the area, and it's the force power of the temperature. That formula you know from statistical physics. And so if you just use proportionalities, then area is 4 pi times Schwarzschild radius squared, and Schwarzschild radius proportional m, so this is proportional to m squared. And this we have seen is proportional to 1 over m, so it's 1 over m to the 4th, which is just minus 1 over m squared. So we have this simple differential equation, dm dt is proportional, I mean, there's some factors, minus 1 over m squared. And every one of you can directly integrate this. This means that t of m is proportional to m0 cubed minus m cubed, where m0 is the initial mass. I mean, you start at some arbitrary time with the initial mass, and then your calculation starts, the radiation, and then mass decreases. So if you wait long enough, then of course the mass becomes smaller and smaller, so you can neglect this. So this becomes, I mean, after some time when m is much smaller than the initial mass, just proportional to the initial mass cubed. So if you have some black hole with initial mass m0, then you know that the lifetime is you find by the third power. That is, if you insert units, so the lifetime I call TBH, the lifetime TBH is then of the order of m0. Of course, what can you have? You have here the Planck mass cube, and you have the Planck time. Yeah. Now you can convince yourself by inserting g's and so on, h bars, that this is basically what you get. And if you insert numbers, then this is around 10 to the 65 m0 measured in solar masses years. So for black holes of the order of solar masses, you see this is at least 10 to the 65 years. Now, do you think this is long or not? Well, you must recall that the age of the universe is about 10 to the 10 years. So this is about 10 to the 55 times the present age of the universe. So this is really very, very long. And so for astrophysical black holes, you cannot expect to see, I mean, this final evaporation. Of course, the mass decreases, and when it reaches the Planck mass, which is only 10 to the minus 5 gram, then Hawking's approximation breaks down. You would then need the full quantum gravity. Actually, that's what we want in that lecture course, that to apply it to such problems, the full quantum gravity. And then it would maybe explode or otherwise evaporate in a final fraction of a second. But to reach that, of course, it takes very long, unless really you have initial masses that are not so large. Just to say that a more precise calculation can be also done. So McGibbon, so she calculated on the basis of the in 1991 of the standard model of particle physics this, and she gave the result that TBH is approximately 6.24 times 10 to the minus 27, and then you have the initial mass cube, and the mass is, I should say, the mass in gram cube, and times a function. Okay, this is, I mean, this is of course the same here, but this function here is just defined as this f to the minus 1, and you calculate from the standard model. If you calculate with all particles, I mean, the black hole is universal, so when it radiates all particles that are there in nature, that are there in the vacuum, and brings them out of the vacuum. Of course, to have pair creation, you should at least have the energy in the radiation to create a pair. Yeah, so the temperature kBT should be at least twice small mc squared, where the small m is the created particle. So of course the black hole always radiates massless particles, photons, gravitons. Long it was thought neutrinos, but neutrinos also have a mass, but a very small one. And when it becomes hotter, it creates other particles. And McGitten has taken all the particles in the standard model, up to 1 tera electron volt, and then you get, I mean, it's not important here now for us. F is 15. It's just a number that you get, which maybe is an approximation for particles in the standard model. Yeah, up to 1 TeV energy. Okay, so what about small black holes? This would be a separate lecture in principle. We can, in principle, generate black holes from density fluctuations in the early universe. Those of you who also attended my early universe class know that early on, if you have inflation, there are also density fluctuations, quantum fluctuations. They have this Gaussian distribution, say, so they are very small. Say what you observe is of here 10 to the minus 5, but Gaussian means that there is always a probability of something very large. So you just do statistics and calculate, if you have a certain model and have a Gauss distribution, how many would you expect from this Gaussian tail here. And so in principle you can produce so-called primordial black holes. So they are not the end product of a collapsing star, and this is why there is a priori no limit to the mass. So they can have a very small mass, and if they are created, in the radiation phase of our universe. No, not the matter, but the radiation phase. And you can, for example, calculate from this formula what initial mass you must have, so that this lifetime is just the age now of our universe, so that these primordial black holes now evaporate today, and you could perhaps see them, this evaporation. And so this is black holes evaporating today. Today means, of course, not on 10th of July or so, but at the present age of the universe. So then you get M0 is around 5 times 10 to the 11 kilogram. This is the mass of a small asteroid. No? So a small asteroid, but which is has the size of an atomic nucleus. No, I mean, this is what black holes are, no? Something very condensed and compact. So, of course, people have investigated that, and it's still a hot topic. So far, I'm afraid I could, if I had time, only tell you about upper limits of this. Yeah, you find the literature upper limit of number of primordial black holes and upper limit of number of evaporations today, because if the black hole is thermal, no? And it becomes then very hot, at the end emits very intense or high energy, I should say, gamma rays. So typically you look for for these events in gamma ray missions like the Fermi telescope and so on. But so far you have not seen an effect of especially this type. So there's only upper limit. And yeah, primordial black holes, they are now of increasing interest because it's still possible that they could yield all or some part of the dark matter in the universe. You know, dark matter from cosmology, something you see gravitationally, but you don't know what it is because it's not baryons. And here, because of the O'Hare theorem, baryon number is not a property of black holes, so black holes do not count as baryonic. So it could be the non-baryonic dark matter. And it's still unclear, depends on the model and everything, but this is a hot topic. It was a hot topic time ago, so we also worked on that some 20 more years ago, but it's again now because of still this window that you have a certain mass window for the dark matter. There are also speculations, I'm not sure whether I support that there is also a black hole nearby. I mean, there are indications for 10th, or now it's called a 9th planet because Pluto is no longer officially a planet. So we have 8 planets, and there is indications that there is something out there, a 10th planet, but not yet seen. And some people speculate that it could be a black hole that circles around the sun at that distance. Of course, it's not seen directly because it's very small. It has planetary masses. I'm not sure how serious this is still discussed with astronomers, but at least that would be something where you could send a mission to, because that's not too far away. So the missions, we have missions already to Pluto, and it's a bit farther away, but in principle, if you have the money from somewhere for this mission, and also the time, it takes some years, then you could check whether there's really a black hole. But of course, if the mission comes too close, then you cannot send anything back because it will be swallowed. Okay, so far for this temperature. Now for that, if you have the temperature, and this is what Hawking calculated, the temperature, then by this here you can calculate the entropy, because this then fixes the factor in front of the entropy. So with TBH we get from the first law that S, maybe write it here, S BH, the black hole or Bekenstein-Hawking entropy, is okay with Boltzmann constants A over 4GH bar. Okay, I should also write here, so I could also write this KB, and you have here A over 2 Planck lengths squared. I could also write it in this form. Now, and you see here, it's clear the Planck length, as was already guessed by Bekenstein, appears here in the denominator. Okay, for Schwarzschild, this is KB pi Schwarzschild radius squared over GH bar. Maybe I have here a C cube for okay, there could be maybe C equals to 1 here and that. So it's 1.07 times 10 to the 77 kb mass over solar mass squared. No? Because the Schwarzschild radius is proportional to mass, then you have mass squared. So that's then the famous formula. I recall that Hawking then also gave that formula then in his article, because after having the temperature, which was 95% of the work, I mean, this was, of course, easy to write down. So he always said that when he dies on the grave, on the tombstone, there should be this formula written, like in Vienna, the tombstone of Boltzmann. You have S is K times the logarithm of the probability, what Boltzmann did. So I have not checked, there was not in Cambridge to check whether really on the tombstone you have this formula. Okay. Now, okay, you see for a solar mass black hole, this is 10 to the 77. This is a huge number. If you calculate the entropy, for example, of the sun, the entropy of the sun is basically the sum of the entropies of all the particles that make the sun, of the photons and protons and the light. And what astrophysicists give is typically 10 to the 57 kb, because it's roughly 10 to the 57 particles, and you know from thermodynamics that there is a direct relation between entropy, density and particle density up to a factor. Now you see if you have something with 10 to the 57 kb and it collapses to a black hole, then you get an entropy of 10 to the 77. So the entropy increases by 20 orders of magnitude. So this is really a huge destroyer of information in a sense. Yeah, so of course you cannot do that. I mean, you can make your disorder in your room at home. This increases the entropy, but it will not increase by such an amount. No? So this is really enormous. No? So this is much smaller than black hole entropy for one solar mass, and it increases quadratically. So the bigger the mass, the higher it is. Okay, so this is in a sense the analog of classical thermodynamics. Yeah, so Hawking and Bekenstein. So there was now no statistical physics a la Boltzmann here involved. So laws of thermodynamics, of course, input from quantum theory, which is of course 20th century, but no statistical interpretation. Of course, this is what people want. So, and this is still an open issue. I will give you one example later, but open is the statistical interpretation of SPH. For example, that SPH can be calculated by the following formula. So minus KB trace rho log rho from statistical physics. Now, okay, I call this the statistical mechanical entropy. This is a density matrix of a certain system, the so-called von Neumann entropy that you know from quantum theory. So when you have a microscopic picture, then you can count these combinations, and in the quantum theory you calculate a density matrix, and you could then call this here then the statistical mechanical entropy, and this should be given to that. Of course, if you have a closed system and that is in a pure state, then this is just zero here. So there must be some coarse graining, as usual in statistical physics, or some neglect of entanglement, or some other approximations, so that you really get an open system. And then you can hope that this. Okay, so in the last 50 or so years, I mean, hundreds of papers have been written on that, and people have given partial results. So it's not purely negative. So in string theory, which I have not discussed in the course, but also loop quantum gravity, geometrodynamics, there are papers where at least suggestions were made how to calculate this from fundamental quantum gravitational entities. Now, I should also mention in this context the so-called problem of information loss. I should at least write it down, and I cannot give you a full account. Problem of information loss. Sometimes it's called the information loss paradox, but it's like the twin paradox. It's maybe a bit too much. It's a problem. And what is that information loss? Now, when if you assume that Hawking's result were exactly valid, not an approximation to an yet to be found quantum theory of gravity, then the radiation of the black hole would be exactly thermal, independent of what you start with. That means any initial state, if it goes to a black hole, will just produce thermal radiation. And this is in contradiction to ordinary quantum mechanics, because for a closed system in quantum theory, entropy is preserved. Either it's zero because it's a pure state, or it has another value, but it will be preserved. So this means that, if true, it would be an uncertainty, as Hawking calls, over and above the uncertainty of quantum theory. Now this has, when Hawking in 1976 first announced this, created much interest and work. And there's still, I see, papers on that that appear. The point is that probably you will have a final answer only if you have a full-fledged quantum gravity calculation of the full evaporation, which we do not yet have, except, say, for models or so. I mean, we would like to really have in quantum gravity a calculation that gives us what happens for a black hole in all of its lifetime until the evaporation. And then there we could see whether it's exactly thermal or not. In fact, the concrete approaches so far in quantum gravity all point to information preservation, because it seems that this semi-classical calculation of Hawking with the Hawking temperature is only an approximation, and that the exact evolution is what we call unitary. A unitary evolution, which is the evolution for a closed quantum system, and the unitary evolution preserves this entropy. So, I mean, the better expression for information loss would be violation of unitarity in quantum mechanics. That's what really is behind. And information loss sounds a little bit better in wider circles, I would say, because information is somehow always fits, but it's sufficiently vague to be defined. No? So, a form of information loss, or more precisely, a violation of unitarity. So Hawking, originally in 1976, argued that information is lost and unitarity is violated, but he changed his mind in 2004. I remember I was at that conference in Dublin where he announced that he believes information is not lost and everything is unitary. He was motivated by some results from string theory, which it seems are not really needed here to argue in favor of unitarity, because whatever you have, and if you have, say, an outside system, so not like we had in the semi-classical approximation, the closed universe where there's no time, but we have a localized quantum gravitational system and we are outside with our classical, semi-classical clocks, then we can check whether, unitarity in our time, semi-classical time, is preserved or not. Yeah, and if it's preserved, then there is no loss of information, and most approaches seem to indicate that this is indeed the case. So that if you look more closely to the microscopic nature of what is behind that, then you will see correlations that that tell you that it's not exactly thermal. Okay, I'm afraid this is a very interesting topic, but today we will not have time to do that, to study this more. I will instead tell you some applications from the usual canonical gravity and also from the loop quantum gravity. So, yeah, I think I still can use that space. So, okay, canonical quantization. Okay, we had two approaches. We had geometrodynamics, and we had loop quantum gravity. And in each of them, various aspects have been studied. I must say, without final consensus, but partial results from particular situations, particular models using particular symmetry and so like. And of course, this is how always physics works. You try to get some insight from special situation, and at the end, you hope you can generalize. So let me first have the geometrodynamics. So you recall we had the ansatz for the metric, which was the 3+1 decomposition. So there was this lapse function and the shift vector, which were three so-called Lagrange parameters, and you have the remaining 6 variables come from the 3 metric HAB. Now we restrict to spherical symmetry and write down this ansatz in case of spherical symmetry. This is the only case where really results were obtained. The realistic case of a rotating black hole, where you have axial symmetry, there are investigations, but it's so far too complicated to get that level of investigation. No? So the ansatz is, okay, minus n squared, the lapse function squared, which only depends now here on 2 variables, because you separate away the angles. And the remaining 2 dimensions are the radial and the time coordinate. So the non-trivial part is 2-dimensional. Then you have some function here called RL. Everyone calls it differently, so here it's called L, dr. And here you have the shift function, I call it NR. So R is not an index, it's just labels that there's one shift function instead of a shift vector that is related to R. And then you have R squared of R and T omega squared. So this T omega squared contains the angles. It's a standard line element on the 2-sphere. And here we have this 2. So out of the 3 metric here, only because of the symmetry, only these 2 functions are left. No? The function in front of this, basically the R squared term, and this curvature radius in front of the omega squared. Now, so that's the lapse function. And this is now only a shift function, not a shift vector. It gives you the freedom to change the R coordinate. Yeah? So you can, instead of R, you can have R bar. Yes? Oh, that this is a mistake. Yeah. Thank you. Yeah, that's clear. Sometimes trivial writing mistakes, but it's good that you keep attention. Oh, if there's in addition an electromagnetic field, so we can describe by the vector potential A, or more precisely, it's a 1 form. So if I write this as a 1 form A, you can write as a phi of R and T, which is a Lagrange multiplier like N and NR. In some gauge, like the Coulomb gauge, it's the electrostatic potential, the Coulomb potential. And then you have here also a function, I call it gamma, in front of dr. So this is a 1 form for a spherically symmetric electromagnetic field. Of course, there are no waves here. It's just a static field. Yeah. Then, if you remember, a central thing in the whole canonical game were these constraints. We had this Hamiltonian constraint and the momentum constraint. So you have then to write down what is here for spherical symmetry. How do the Hamiltonian constraint look like? How do the momentum constraints look like? This is, of course, in principle not difficult, but it's in the details a little bit lengthy, and it has been calculated, of course, long ago by people, so it's a kind of standard result. So we have here the constraints. Now, without additional matter fields, just the vacuum, so you have H orthogonal is g over 2, the gravitational constant L, PL squared over r squared. So PL is the momentum conjugate to L, minus g times PL times PR over R plus L P gamma squared, if you have this electromagnetic field, over 2R squared, plus g to the minus 1, and then you have the potential is vanishes as a constraint. No? So you have here, as in the full constraint, you have the gravitational constant here, and here you have the inverse of the gravitational constant. Yeah, this you can also give explicitly. I can write it down, but today we will not need it. But you can write it down just to see how complicated it looks like. Yeah. Okay, the momentum constraint is now only one. I'll use the singular high HR. It's only the one that is related with the r degree of freedom. No, it's related with the coordinates on the three-dimensional space, but two are angles that are frozen, so only the radial part is flexible. So you only have this HR, and it turns out to PR r prime minus L PL prime. Yeah. And it just means that this that R and PR transform as scalars or as scalar densities. And there's also the Gauss law, now the standard Gauss law from electrodynamics, which is just P gamma prime equal to 0. So that's of course a very restricted Gauss law, because we just have spherical symmetry, and this is what usually is the electromagnetic field. This would be divergence of E, but from the divergence we just have the prime for R, and the P is just one component of the electric field. Okay, so one thing is to of course now work with this. I mentioned something about that in a minute without doing calculations. You can also, in that simple case of spherical symmetry, employ the reduced quantization. Recall what is reduced. This is when you can solve the constraints classically and then only quantize. And this is what Karel Kuhasch did in 1994 for the spherically symmetric black hole, and other people then extended to electromagnetism. And at least there you have some explicit results, although it's just a pure black hole without matter. So it's not that you can do many things with it, because you also want to have interaction with matter. So this is a paper by Karel Kuhasch from 1994, and he had a reduced quantization of a Schwarzschild black hole without other degrees of freedom. So the situation is that you have that black hole there, spherically symmetric, and of course there's an outside universe. It's not a closed universe, so you have maybe far away observers. You have asymptotic flatness, and far away from the black hole then you have again your standard parameter, such as the time, the semi-classical time that is far away from the black hole. And the black hole is considered here as a localized quantum gravitational object. It's not that the whole universe here is quantized. And so they are bound from boundary terms. He gets then this time. So this is a very short summary of a very, very long paper from boundary terms. You have tau and lambda. Okay, the lambda was then introduced by, this has to do with electrodynamics. So in Kuhash's case, the black hole was uncharged, but later people have added, I mean, the spherically symmetric, I mean, the Reise-Nord Stream case. So they are additional variables. So this is the proper time at infinity, if you like, at infinity or far away. This is what infinity means, and which is conjugated to the mass of the black hole. So tau and m in this formalism with the boundary are conjugate variables, quantized, and this here is conjugate to the electric charge. And Kuhash then boiled the whole formalism by, you have seen, I mean, how the Hamiltonian constraint looked like. It's a long expression. So by many canonical transformation, he could make this problem, I mean, without matter, feasible. And he could have he arrived at simple constraints. So this is, C tau is defined as pi tau plus m, which is the constraint, and C lambda is defined as p lambda plus q as a constraint. So that looks very simple, no? So the work was to arrive at this and to justify it. I mean, when I give this to you, as a result, of course, you can immediately quantize, because you just apply this on wave functions, set it to 0, and these are the momentum are h bar over I derivatives. So quantization is then h bar over I d psi over dt plus m psi is equal 0, and h bar over I d psi over d lambda plus q psi is equal to 0. These are the constraints that are left. So somehow, because of spherical symmetry, the black hole has no really other degrees of freedom, because the symmetry is frozen, and also there's no matter, so the black hole cannot emit Hawking radiation and the like. This is why this is possible. I mean, you may be puzzled that you arrive at such a simple result, but this is because of the simplicity of the system. And this you can solve, of course. I mean, and you have then the wave function, which depends on tau and lambda only, is then, okay, some function that you can m and q, and then you have e to the minus I m tau plus q lambda over h bar. No, so a plane wave type of solution. There's no gravitational constant. It's not that this is hidden in gm, so m has here the dimension of 1 over length, like in particle physics, just from h bar. I mean, m over h bar has dimension of 1 over time. Well, c is, of course, set equal to 1. Yeah. So one can also add another degree of freedom, and later after Kuhash and here people who did that, one has also more investigated here the structure here in the Goskal diagram, this bifurcation point of the horizon, and found that, I mean, in the canonical formalism, I mean, if you have here a hypersurface that goes through here, yeah, that also here you need some boundary conditions in the formalism. So need boundary conditions. So in the same way as you have them at infinity, asymptotically. Also here, because for the outside, I mean, you only have this here. And so if you have a surface that originates there, you have also to have a boundary condition, and you arrive at a new constraint. I mean, I'm sorry, I mean, it's difficult to motivate this without derivation. I can only say the following. It's similar to here where you have boundary conditions from infinity, that give you this remaining constraints. Here also, in that case, you have a boundary condition at this what is called bifurcation point, and this boundary new constraint it's called C alpha, and it's pi alpha minus then the area over 4 pi g. So now what is alpha? Alpha is called rapidity, because it has similar properties like the rapidity in special relativity. You know that perhaps from special relativity, which is related to the velocity or velocity over c, and I think the hyperbolic tangent or something of that. And so you find then here, if you take this into account, you find then for the total wave function psi of alpha, tau, and lambda is chi of m and q, and then you have an additional factor I over h bar a of m and q times alpha over 8 pi g minus m tau minus q lambda. What you can do, for example, with that is, you can construct the wave packets like you do the wave packet of the free particle in quantum mechanics. You have with a Gaussian, and then study, whether this wave packet has a dispersion or not. In fact, you find that it will if you have start with a Gaussian wave packet, it will disperse, and the dispersion will be noticeable at a time proportional to the initial to m cube. Although this has nothing to do with Hawking radiation, somehow the same m cube comes here. So the same lifetime. So if you prepare this black hole as like a localized particle you prepare, then you also have to wait very long until this disperses. But there may be no dispersion at all, because this is here we treat the black hole as a closed system, and in the real world, of course, it interacts with other degrees of freedom that may prevent the dispersion. Now, in this context, the entropy of black holes, what people have done, and I think this goes back to Hawking and his formalism of Euclidean quantum gravity. If you remember chapter 2, we had these path integrals. I mostly did the Lorentzian path integral, where you sum over all metrics with an e to the I, the imaginary unit action over h bar. But many people have discussed Euclidean version, so that you rotate, so-called Wick rotate, the time to an imaginary quantity. You have the t goes to minus I times the tau. And there are pros and contras for doing that. And this you can also do here. You have a Euclidean version, which means that tau, you go and you set them, because you know from statistical mechanics Euclidean time has to do with temperature. So beta is 1 over k times the temperature. And you can the lambda, that's not seen directly. I just give it to here. It has to do also with that. And the alpha is very interesting, because the alpha, when you go to a Euclidean version, you check the line element, and you find, and this is also what I think Hawking found in the 1970s, you find that the line element is only regular if this alpha or Euclidean is chosen to be 2 pi, because of regularity of the Euclidean line element. And if you do that, then you could write down, I mean, a Euclidean wave function of alpha tau lambda. I don't add here the indices E, which is chi of M and Q. And you have exponent of A over 4GH minus beta M minus beta phi Q. No? Okay, so that's what you get here. And okay, there's something to be observed. Okay, this minus beta M is something that reminds one at partition sums in statistical physics, but what you see here, the emerging, this is just the expression here for the entropy. Now is this just an accident? Okay, you now know in this field that there are not so many accidents, and that there's not an accident that you also have the correct factors and here everywhere. So in fact, this is can be interpreted as an enhancement factor for the rate of a black hole pair creation relative to ordinary pair creation. So we have just more enhancement of a production rate because you have this entropy factor, which gives you many more options for that. No? So here, so this is an enhancement factor for the rate of black hole pair creation relative to the ordinary pair creation. For example, if you like a comprehensible account, I mean Hawking and Penrose in their book The Nature of Space and Time give an explanation, also with many pictures here on that. Or can also read a German translation of that if you like. So somehow you get here, and also you get the same from the Euclidean path integral. And in a sense, it's much shorter calculations than these original calculations of Hawking. Okay, I did not give it, but this is quantum field theory in curved space-time. And you have, for example, to deal with the non-uniqueness of vacua, the initial vacuum, the final vacuum pair creation. You have so-called Bogoliubov coefficients. So this is a very long and complicated calculation. And when you do it first time, I mean, you spend days before you get what is done there. But with this Euclidean approach, it seems to fall, I mean, from heaven somehow. And the argument why this seems to fall from heaven is that, okay, the Euclidean version is very close to thermodynamics. I mean, you learn that in statistical physics, that you get partition sums and all that by having tau t going to minus I tau, and identify this with 1 over kt. Or you have this beta, which is 1 over kt. So there's this formal equivalence, but you don't get too much new insight into that. It's just that the formalism is consistent. If you have one Lorentzian approach and say standard quantum field theory, complicated but I think straightforward at the end, and then you have this formal Euclidean path integrals that relate to thermodynamic. And of course, this should be consistent. This is why you find these results, at least this temperature and entropy, without really understanding where they come from. And they come also from these wave functions, for example. And in the literature, there are in fact many, many papers where you can derive entropy and temperature from different angles. And so this has not been observed, this temperature entropy, but because you have so many derivations from different sides, this is why people regard this as something very sound, even if it's not yet observed. But it's all at that level of non-statistical mechanics here. That's not yet density matrix and von Neumann entropy and the like. Now time is approaching to an end, but I would like to show you at the end, I think, two things. First is Yeah, an idea that black holes, if they are treated fully quantum, they are maybe a bit like atoms. They have a spectrum, discrete levels. And then the other thing is related to that, whether we can calculate this from loop quantum gravity. Okay, so I think in the last 10 or maybe if you allow 15 minutes at most, then we will do that. So I could call this spectroscopy of black holes. Okay, I can give here a question mark. Here it's not yet as established as atomic spectroscopy. And it also goes back to a seminal paper by Begenstein in 1974, and there's an extension of that with more details by Begenstein and Mukhanov in 1995. And yeah, so what do they do? Okay, it looks very simple, but nevertheless, I mean, there is an important point to it. I mean, they make an Ansatz, an ad hoc Ansatz. So, ad hoc Ansatz. And they assume that the area is quantized, that maybe loop quantum gravity gives this, or geometrodynamics gives this. We shall say later see what loop quantum gravity gives, but you can make an assumption and study consequences. So you can make the assumption that the area is quantized, area of the event horizon, and I call this AN with a to be determined factor alpha. It has nothing to do with the alpha here. Now we are a different context, LP equal N, so that this is discrete and equidistant. Okay, this is just an Ansatz, and we don't know whether this is true. This is just a natural number. Okay, this sets the scale. You don't have anything else than the Planck scale. So what could you write? No? Of course, you could write an n squared and check it, but let's do that. So a bit like the harmonic oscillator. So the energy state that corresponds then to n, we assume it be degenerate and has a certain multiplicity that we then demand to be equal to the entropy. No? So demand that the entropy, this is what we want to understand, A over 4 LP squared, which is SPH, plus potentially some constant, is equal to the logarithm of ln g of n. So this is a multiplicity. So you have the state has multiplicity, so degenerate. No, you have many states for the same energy level. And of course, I mean, for the assumption is that G of 1 is 1, so this should be the ground state, and we assume that it has no degeneracy. So no degeneracy of ground state. Okay, so then if we insert that here, then we have here alpha times n over 4. No, you insert here this at that point, call it alpha n over 4, plus a constant is the logarithm of g of n. So for n equals 1, this gives alpha 4 is minus the constant. And so get from this that alpha 4 times n minus 1 is the logarithm of g, and this is the entropy. So it's a kind of microcanonical ensemble. No? It's just the logarithm of the number of states. And from this you get g of n is e to the alpha n minus 1 over 4. Okay, then this must, but this is a multiplicity, so this should be a natural number. So this is a natural number if alpha is 4 times the logarithm of k, with k is 2, 3. Now if you insert here alpha is 4 times a logarithm of k, then okay, it cancels this, and then this gives you then a real number, a natural number. Now what is k? Okay, the simplest would be k equals 2. And then you get an is 4 times logarithm of 2 LP squared times n. Well, this resembles older ideas of John Wheeler called it from bit, where he has the picture that, okay, we do not know the microscopic degrees of freedom of a black hole, but we can imagine the following, that we subdivide the area of a black hole into Planck length squared little areas and randomly distribute ones and zeros on it. No? And then you have just two possibilities, and this would correspond to that. No? So that's his picture. So you have here this, and you have here you subdivided it. So this is the black hole, the area, and so this is here of order Planck length squared, and then you distribute here ones and zeros here. 1, 1, 0, 1, 0, and then you count the numbers, no? And so on. And this would give you a measure for the entropy. That's the picture what is behind. Of course, he doesn't explain what gives you these bits. So this he called it from bit. It from bit. Well, he was very good in language. I mean, coined black holes and others, and no hair. So it from bit means bit these alternatives, and then you get the black hole or whatever. If we look into the Schwarzschild case for that, if we have this, I mean, then what consequences can we draw for radiation? So the Schwarzschild case. So we have A is 16 pi gm squared. No, I mean 4 pi Schwarzschild radius squared, and Schwarzschild radius is 2 gm. So from this you get then delta A is 32 pi g squared m times delta m, and this should be, according to our law, 4 ln k times p squared, keeping k general here. And then you get from this that delta m, which is the same as delta E, because mass is energy, and we call this as an h bar omega k tilde. I mean, a certain fundamental frequency or angular frequency is connected with that. And so this then is h bar ln k over 8 pi gm. So this here would then be a fundamental frequency for such a black hole. Fundamental frequency omega k tilde is a logarithm of k over 8 pi gm, which is logarithm of k times the black hole temperature over h bar. So the black hole, if this is correct, then has certain energy levels that are distributed by this formula here, delta m, and you have these frequencies that maybe if you have a transition between these energy levels, that is then what would be emitted, say in photons or other particles. But what you see, you would get a discrete spectrum here, which is not like Hawking radiation. Hawking radiation is continuous, it's a thermal, a Planck spectrum. So even for the mass much bigger than the Planck mass, so for astrophysical black holes, you would have a discrete emission spectrum. And in fact, as you see from this here, this omega k tilde is the same order as the maximal frequency in the Planck spectrum. So you definitely have, of the Hawking temperature, so you definitely have a totally different picture for such a case, which you, if you could observe, you would immediately see whether this is correct. You have a discrete spectrum, so spectral lines, or you have the Planck spectrum. So this is would give you a discrete emission spectrum, so unequal Hawking radiation, even for m much bigger than the blank mass. And for example, quanta with omega smaller than this omega k, they could not be absorbed from the black hole, no? Because they would not fit the difference between the levels. So you could send, but this strange quantum black hole does not even allow to absorb it. Classically, it swallows up everything, but here it would not allow to absorb because you would not fit the distance between spectral lines. Now, in loop quantum gravity, people have tried, for example, to calculate the discrete spectrum by their formalism, and this was an assumption. No? It's a toy model, and everyone who knows a little bit about thermodynamics and something can understand what is going on. But the loop quantum gravity from last time, you remember there were these spin networks and these discrete graphs and so on. You can, using their combinatorics, you can try to identify them with the bits of Wheeler and counting in an appropriate way. So that's the last thing. Black hole entropy from loop quantum gravity. I mean, we have the picture. We have, say, here a two-dimensional surface called S, and we have a spin network. Well, we have a spin network consists of many graphs, and one representative is maybe this, but you have many of them, and they have these spins on it, no? Ji, so it can be 1/2, 1, 3/2, or whatever. So, and we now consider the cross section of this with the horizon surface of a black hole. No? So consider crossing of spin network with event horizon of a black hole. Now, because these are spins, then the dimension of the corresponding Hilbert space for each spin is 2J plus 1. This you know from quantum mechanics. So the dimension of all of this is then the product of all these dimensions. So dimension of Hilbert space, then the product from I equals 1 to n to Ji plus 1. Now we had in last time the result, well, I only quoted it and I tried to illustrate it, but I did not derive the so-called area spectrum in loop quantum gravity, that areas are quantized. And this is of course used here. So we had quantization of area, and we had this result. So we have the area operator of a certain surface, which we take here the surface of the black hole, and we have the spin network state that depends on A, and it was 8 pi beta LP squared, and the sum then over all crossing points P that follow from the spin network, I mean cutting the surface, so that would be here a point P, one example, but can have many points. And then, so we have square root of JP times JP plus 1 times psi S of A. Okay, this looks certainly different from the Bekenstein-Mukhanov spectrum here, no? And it's not so simple. It's not just an N. It has this and fortunately, because here you find that if you have the spectrum of this here, that the consecutive energy levels become closer and closer, or area levels become closer and closer together. So there is no contradiction to Hawking radiation for large black holes. I mean, in an equidistant spectrum, I mean, that's different. Yeah. So I don't have time to give you the calculation. What is done is, I mean, one uses a minimal spin first, so the minimal spin, and so I mean, say 1/2, and then we would have the corresponding area would then 8 pi beta. This is this Barbero immediacy parameter we had, LP squared square root of J min times J min plus 1. And the original assumption of the people who did that was to assume that this gives the dominating contribution to the end ratio, or only count them. So there were some nice calculations beginning of this century with some results, and you see you have here this free parameter in loop quantum gravity, this Barbero immediacy parameter, which is just a number. And if you calculate the entropy from the combinatorics, the entropy depends on beta, naturally. So what can you do? You can say, okay, we really firmly believe in Bekenstein-Hawking result. We put this equal to the Bekenstein-Hawking entropy. Actually, the proportionality to A comes out. That's okay. But the prefactor depends on beta. But if you say, okay, the prefactors should be this 1/4 GH bar, then you can fix the beta. And then you can say, okay, now we're fixed. Now we go to other observations and results and use that value of beta. And so originally people thought, yeah, so we just choose jot min is equal to 1/2. And then actually it's 3-4 lines. It's in the book. It's just, I cannot do it here, but here you find this value, which in a sense is nice because it also has this bit factor logarithm of 2 and so on. But unfortunately, it turned out that this is not correct because the assumption is not true that only minimal spins count, or that they give the overwhelming contribution. People have then checked what can you find if all the higher spins are taken, and found that they cannot be neglected. No? So this is an unrealistic assumption. But this is an unrealistic assumption. So things are not always as nice as one would like to have them. So the higher spins are essential, and the combinatorial problem, I mean, just to count, I mean, how many crossings and so you can have, turns out to be complicated, and results in an equation for beta that you can also only solve numerically. No? Higher spins, higher than 1/2, higher spins are important. And if you take them, then you find the following equation for beta. I mean, from the demand that you get Bekenstein-Hawking formula. Yeah, so this is something, and you must, this is the equation for beta, and you must solve this for beta. And Krzysztof Meissner in Poland has done that. So numerical solution for beta. Yeah, and you can only give a result. Okay, beta is 0.237. Okay, to the accuracy you like, you can give that. So that was the result then of Meissner in 2004. And so how do you interpret this? I mean, is this really the fundamental Barbero immediacy parameter of loop quantum gravity? No one knows, because we have so far no second test of loop quantum gravity, where we could then use this value and see, then it comes out correct. So this is still an open issue. So I mean, it comes out, and I think the calculation you can follow. So if you believe in these spin networks and if you believe in this here, then it's a pure mathematics to do that. And if you demand that to be equal to the black hole entropy, which almost everyone does, then that's the result. But it's not clear. Now, just one final remark here to this here. Here you see here, going back to here, this is with the Bekenstein-Mukhanov spectrum. So if you have here, say, k equals 3 instead of 2, we have omega 3 tilde is the logarithm of 3 over 8 pi gm, which is the logarithm of 3 over h bar times the Hawking temperature, and which is roughly 8.85 solar mass over mass kilohertz. That would be that fundamental frequency of this quantum black hole. And it's very interesting that there seems to be a connection to what is called quasi-normal modes. Now that's something people discuss in black hole physics for quite a while for classical black holes. Because a black hole, I mean, it emerges from collapse, but before it is stationary, it oscillates and emits gravitational wave, and it's like a bell that you hit, and that has this damping overtones. And in the black hole case, they are called quasi-normal modes. Quasi because they are damped away. It's not just sine and cosine. And so the question is whether there is a connection of this with the quasi-normal modes. Yeah, because these modes one can prove, I mean, for very large n, but the spectrum of these modes for large n is, it has this damping term, with an I, and then it has a real term, and there again a logarithm of 3 appears, and higher orders. So has this any relevance also for this consideration or not? What I could show 20 years ago was that when you make a quantum measurement of this quantized normal modes, then you introduce what is called a noise temperature in quantum optics, which is just a Hawking temperature. You find this logarithm of 3 will cancel this logarithm of 3, and we are left with the Hawking temperature. So in a sense, you could have again another way to the Hawking temperature, although it's not so clear intuitively. Now, this more or less finishes this introduction and appetizer. You see there are many things and many open things where people are working on, and where also young people are encouraged to work on, perhaps more formal thing and more physical Gedanken experiments, but the program is far from finished. So the two major issues to be solved by quantum theory of gravity is, of course, to give a microscopic interpretation of the entropy, maybe along these lines or along other lines of string theory, which I have not discussed, and to discuss the full evaporation of a quantum black hole. So it emits Hawking radiation, it shrinks, and what happens at the end point? And how can you observe that if you have primordial black holes? So these are the two crucial questions, and everyone who can solve at least one of them, I think his or her fame is guaranteed. So with this I conclude the black holes, and next time we have the last session. So we go from black holes to the universe as a whole, quantum cosmology. See you next time.